1. Why quantum computers could threaten Bitcoin and blockchain. Cryptographic vulnerabilities. Bitcoin and most blockchains rely on cryptographic algorithms, particularly elliptic curve digital signature algorithm, ECDSA, used to secure private keys and validate transactions. SHA-256, hashing, used in mining and generating Bitcoin addresses. Quantum computers could theoretically break ECDSA using Schur's algorithm to derive private keys from public keys, enabling theft of funds. Potentially reduce the effectiveness of SHA-256 for mining and validation processes. Speed. Quantum computers are exponentially faster at solving certain problems, which could allow an attacker to outpace traditional miners or disrupt consensus mechanisms. 2. Current limitations of quantum computers. Insufficient qubits. Breaking ECDSA or SHA-256 requires a quantum computer with thousands, or even millions, of high-quality, error-corrected qubits. Current chips, like Google's Willow, 105 qubits, are far from this capability. Error rates. Quantum systems still struggle with noise and error correction, making them unreliable for such large-scale attacks. 3. How blockchain could adapt. Quantum-resistant cryptography. Researchers are developing quantum-resistant algorithms, also known as post-quantum cryptography, which are designed to resist attacks from quantum computers. Blockchains can adopt these in the future. Examples include lattice-based cryptography and hash-based signature schemes, soft forks and upgrades. Blockchain networks like Bitcoin can implement protocol upgrades to transition to quantum-resistant algorithms, although this requires community consensus. 4. Timeline of quantum threat. Experts estimate that quantum computers capable of breaking Bitcoin's cryptography are at least 10 to 20 years away, depending on advancements in quantum hardware and error correction. 5. Broader implications for blockchain. Security risks. Until quantum-resistant solutions are widely adopted, blockchains will remain vulnerable to advanced quantum attacks. Opportunities. Quantum technology could also enhance blockchain, enabling faster consensus mechanisms and more efficient cryptographic operations. Conclusion. Quantum computers pose a theoretical threat to Bitcoin and blockchain, but the technology is not advanced enough to exploit these vulnerabilities today. As quantum computing progresses, blockchain developers and communities are already working on quantum-resistant solutions to safeguard against future risks. Upgrading blockchains to become quantum-resistant is a critical step in preparing for future quantum computing threats. Here's a breakdown of how these upgrades might work. 1. Key components of blockchain vulnerable to quantum computers. Public key cryptography. Used in transaction validation and wallet security, for example, ECDSA for Bitcoin and Ethereum. Hash functions. Protect the integrity of data, for example, SHA-256 in Bitcoin. Any upgrade must replace these cryptographic primitives with quantum-resistant alternatives. 2. Quantum-resistant cryptography. These algorithms are designed to resist attacks from quantum computers. They form the backbone of blockchain upgrades. Lattice-based cryptography relies on problems like the shortest vector problem, believed to be resistant to quantum attacks. Algorithms NTRU, Kyber, chosen by NIST as part of its post-quantum cryptography standardization process. Hash-based cryptography uses cryptographic hash functions for digital signatures. Example, Merkle signature scheme, MSS, or XMSS, extended MSS. Multivariate polynomial cryptography relies on solving multivariate quadratic equations. Code-based cryptography, based on error-correcting codes. Example, Macaulay's cryptosystem, Isogeny-based cryptography. Based on elliptic curve isogenies, less common but promising. 3. Potential blockchain upgrade approaches. Upgrading blockchains to quantum-resistant cryptography can follow several paths. A. Hard fork. What it is: a permanent divergence in the blockchain, requiring all nodes and users to adopt new software. Use case: if the existing cryptographic system is replaced entirely. Challenges: requires network consensus. Disagreements could split the community, as seen with Bitcoin Cash. B. Soft fork. What it is: a backward-compatible upgrade where older nodes can still validate new blocks. Use case: adding quantum-resistant features while maintaining compatibility with older cryptography. C. Gradual transition. Allow users to migrate to quantum-resistant wallets and transactions over time while supporting legacy cryptography. Example: introduce quantum-resistant keys alongside traditional ones and incentivize their adoption. 4. Specific changes in blockchain protocols. New signature schemes. Replace EXA with post-quantum algorithms like XMSS or dilithium for wallet and transaction security. Quantum-resistant mining. Replace SHA-256 or similar with hash functions proven to be resistant to quantum attacks. Multi-signature and threshold schemes. Use quantum-resistant multi-signature systems to improve transaction security. Key rotation. Encourage users to regularly update their private keys to quantum-resistant versions. 5. Examples of blockchain projects working on quantum resistance. Bitcoin. Some developers propose transitioning to quantum-resistant cryptography, though no consensus exists yet. Ethereum. Plans for continuous protocol upgrades could include post-quantum algorithms as part of future forks. IOTA already integrates quantum-resistant hash-based cryptography for transactions. Algorand, researching quantum-resistant algorithms as part of its long-term roadmap. 6. Challenges in implementing blockchain upgrades. Community consensus. Decentralized governance makes upgrades complex, as changes require agreement from a majority of users and nodes. Computational costs. Post-quantum algorithms are often more computationally expensive than existing ones, potentially impacting scalability. Backward compatibility. Ensuring older wallets and nodes can still function while supporting new cryptographic methods. Testing and security. New algorithms need extensive testing to ensure they are truly secure and efficient. 7. The timeline for upgrades. Most experts believe quantum-resistant upgrades will be necessary within the next 10 to 20 years, as practical quantum computers capable of breaking existing cryptography become a realistic threat. Conclusion: blockchain upgrades to quantum-resistant cryptography are feasible and already being researched. However, they require proactive planning, extensive testing, and community consensus. These upgrades will ensure that blockchain technology remains secure in the quantum computing era.